In this video, we are going to demonstrate how to simulate in MatCalc the aging process in aluminum-based alloy of 6000 family. The aging process is quite complex, and it is not fully understood. So we will actually simulate one of the scenarios considered as taking place in the material. We will simulate first an isothermal holding at the room temperature, starting from the solution anode material, which will be quenched to the room temperature. Next it will be held at the room temperature, so that some natural aging processes will occur in the system during which the co-clusters of magnesium and silicon form. Afterwards, we'll heat up the material to some elevated temperature and hold it at this temperature for some time. This will be the stage where the artificial aging occurs, and the strengthening phase, which is some sort of beta double prime phase, develops out of the co-clusters formed previously during the natural aging. The co-clusters transform then to the strengthening phase beta double prime.
The very first thing in MatCalc is of course the creation of the new workspace. In Menu File, I click on New and create now a new workspace. The very next thing is opening the thermodynamic database and reading the data relevant for our simulation. Click in the menu Global, Databases. We will simulate the aluminum base alloy. So we are definitely interested in some aluminum-related database. Click on Open button. There is an MCAL database. Let us open that. We see that aluminium is already selected here. Solute elements for 6000 alloys will be for sure magnesium and silicon. So I select these as well. The phases we are going to consider in our simulation would be the FCCA1, which represents the matrix phase. We will need some co-cluster phase for the natural aging step. And for that, we take the CLMGSI phase, which represents the early metastable magnesium-silicon co-clusters. Then we'll need a phase representing the strengthening beta double prime phase. There are a few phases, which we can take for that. There is the beta DP1 which contains some aluminum. There is the MG5SI6 beta double prime which is just a binary phase with no aluminum. Let us take the phase AlBDP, which is a metastable aluminum containing precipitate phase in the beta double prime precipitation regime.
Next, read the data relevant for these phases. Of course, we are doing the kinetic simulations, so we need some data for the mobilities of the elements that we have selected. Let us read the diffusion data. We are interested in the aluminum database, MCALDDB. Let us open it and close this window. The next thing is the definition of the alloy composition. Let's go to Menu Global, Compositions. We get the window with the elements list. Switch to weight %. The composition we are going to analyze will be 0.7% for magnesium and 0.4% for silicon. This composition would correspond approximately to 6063 alloy, which is commonly used for the extruded parts. As we can see, the aluminum content is balancing the content of the solute atoms of magnesium and silicon. Having set this composition, press OK. I prefer always to calculate some initial thermodynamic equilibrium. It's not required for the kinetic simulation, but I have this habit to check if we get a reasonable thermodynamic equilibrium result. To do that, go to Menu Calc, set Start Values, which initializes the system, and calculate an equilibrium. Take 180 degrees Celsius as temperature relevant for the artificial aging and click on Go. As we can see, there is the equilibrium between the FCCA1 and the AlBDP phase, which is the hardening phase. Co-clusters are not stable at this temperature.
The kinetic simulation needs few more definitions. The first one will be the precipitation domain. Then we need to define some precipitate phases. Last we define also the temperature time program. Let us start with the precipitation domain. We need to create a new domain and specify a name for it. I will just call it matrix here. The thermodynamic matrix phase taken for this precipitation domain is FCCA1, our matrix phase. Lower the initial grain diameter from current 100 micrometers to 50 micrometers. The smaller grain size would correspond to the little bit faster diffusion. The smaller the grains, the more grain boundaries we have in the structure, and the mean diffusivity in the matrix will increase. What we definitely need for the aging simulation of aluminum-based alloys is some evolution model for the vacancy concentration in the system. Go to the MS Evolution tab. In the sub-tabs, there are various microstructure elements. Go to the vacancies. This is what we are interested in. Currently, there is no vacancy annihilation generation model selected. So, let us select FSAK Vacancy Dynamics instead and leave the default settings. The next thing which will be relevant for our simulation is the trapping of the vacancies. Our model describes the vacancy diffusion towards the sinks. Starting from the solution in yield state, the vacancies which are present at the elevated temperature annihilate with decreasing temperature by reaching the sinks as described by the FSAK model. But these vacancies will meet some traps on their way to the vacancy sinks, slowing down the annihilation process. We define now these traps in Trapping tab, within the FSAK Traps tab. We add a new trap, which becomes an index of 0. What will be trapped are the substitutional vacancies, abbreviated here with SV. One of the trapping sides would be the magnesium atoms in the solid solution, so select Mg as site. Next we need a trapping enthalpy. Some data from literature suggests the value of around 5 kJ per mole of magnesium atoms. So type 5000 here, as the value is expressed in joules per mole. Add another trap for the vacancies, which will be the silicon atoms in the solid solution. The value taken here is 7.2 kJ per mole, so type 7200. Another trap existing in the system are the co-clusters that would form during the natural aging. But in order to define those, we have to define first the co-cluster precipitate phase. Close the precipitation domain window for now. And let us proceed to the phase status window, where we define our precipitates. Select the two phases, the co-cluster and beta double prime phase, and create the precipitate phases out of them. Now, we define some settings for the phases.
Let us start with the co-cluster phase. The co-cluster phase is difficult to model it properly, because it is on the border of precipitate definition. On one hand, the clusters could be still regarded as a bunch of solute atoms that come together, on the other hand still comprise a part of matrix. So, in our approach we treat these as precipitates. In order to represent their high number density, we have to modify the interfacial energy. Go to the Precipitate tab. Modify the interfacial energy calculated by MatCalc, by adjusting for the diffuse interface effect, because the boundaries of the co-clusters could in principle contain some aluminum. The diffuse interface effect will be expressed by definition of the regular solution temperature, with the value of 800 Kelvin. This setting influences nucleation of the co-clusters. The next important setting for this phase is located in the Special tab, and it treats the precipitate coalescence. It relates to the fact that the co-cluster growth will not be limited to the diffusion of the single atoms from the matrix to the available clusters, but the co-clusters themselves will also move a little bit around their position and by chance, they could also collide with each other. Once two co-clusters collide with each other, a bigger precipitate will form out of these. In order to cover it, choose the model, Binder-Stouffer Dynamics. For precipitate coalescence, where the diffusion of a cluster is described as the function of cluster volume, with an exponent of -4/3 and the prefactor of 30. Let us go to the next phase, the aluminum containing beta double prime as mentioned before in our scenario. This phase will come from the available co-clusters, formed during the natural aging. Go to the nucleation tab and switch nucleation model from classical nucleation theory to particle-related transformation. Add the source precipitate from the list, which is the co-cluster precipitate phase, and click OK. Among the few nucleation options available, select equivalent interfacial energy and specify the interfacial energy which will not be calculated directly from the thermodynamic data of the beta double prime phase in this case. The value for this transformation is taken as 70 mJ per square meter, which corresponds to 0.07 joules per square meter. One more adjustment that we will do is the definition of the minimum nucleation radius. As the beta double prime structure has to be of some minimum size and is definitely greater than 1 interatomic, distance 3.5 angstroms is given here by default. We will take a value of 2.5 nanometers here. Go back to the precipitation domain window, and set a new trapping site which is the co-cluster precipitate. Add another trapping site for the substitutional vacancy, which will be trapped on the co-cluster precipitate. The trapping effect of co-clusters is quite strong with the trapping enthalpy of 24 kilojoules per mole, corresponding to 24,000 joules per mole.
Let us define our thermomechanical treatment in global menu. Create a new treatment, we call it aging, and click on OK. Create a new segment and double-click on it, in order to enter the segment editor. We start with the solution annealed structure, so take 540 for start temperature. As we quench the material to the room temperature, take end temperature, and heat or cooling rate as controlling parameters. The end temperature will be the room temperature of 25 degrees Celsius, and the cooling rate of 100. On the right, select matrix as a precipitation domain. Create a new segment. The start temperature is already at 25 degrees Celsius, which is the end temperature of the previous segment. Switch to heat and cooling rate and delta time. Heat and cooling rate would be 0 corresponding to isothermal holding. Let us simulate a natural aging period of 1 week. This will be represented by 7 days times 24 hours times 60 minutes times 60 seconds. That means that the material after quenching just lies for 1 week before it is processed further. After this week period, the artificial aging process starts. Create a new segment. Take 180 degrees Celsius, which represents a typical temperature for artificial aging. For the heat cooling rate, take 1 Kelvin per minute, which is 160 Kelvin per second. Proceed with another segment. Again, select heat cooling rate and delta time. Take 0 for heating cooling rate. Delta time will be taken as 24 hours. Type 24 hours times 60 minutes, times 60 seconds. Let us review our segments once again. Starting with quenching to room temperature after solution annealing. Followed by holding it for 1 week at room temperature. Next heating it up to 180 degrees Celsius with 1 K per minute, and last holding it for 24 hours.
Let's create now the plots which will describe the precipitate state of the material. Create new window by clicking on the shortcut icon. Let's create now the plots which will describe the precipitate state of the material. One could create the plots one after another, creating the individual plot core, XY data window. But for this typical presentation of the precipitate state of the material, some user-defined scripts were already included in MatCalc, which deal with this task. Therefore select the fourth item in the list, 03 kinetics, 4 frames, where the frame contains 4 plots. These will show the time evolution of the system, the phase fraction of the precipitates, their number density and mean radius. In this frame these will be depicted over the linear scale for the time parameter. I will maximize the window size to get a better overview of the created plots. One can notice 4 plots having all axes already described accordingly. Also the series for the created precipitate phases can be seen in the legend.
Start a simulation in MatCalc. Precipitation kinetics. Check if the thermomechanical treatment defined previously is selected. All other settings can be left on their default values. Click on Go. The calculation proceeds. The quenching is already done. We are holding the material at room temperature. The green line which corresponds to the co-cluster phase is present on our plots. So it's nucleated already. The radius is increasing. So is the phase fraction. Notice a small decrease of the number density that corresponds to the coalescence of the material, where the clusters are colliding with each other and form bigger ones. The temperature rises now 180 degrees Celsius and remain at this value for 24 hours.
It is time for an analysis. The temperature time profile is defined by ourselves and is not that interesting. In phase fraction diagram, there is a formation of the co-clusters during the natural aging period. With increasing temperature, the co-clusters are transforming to beta double prime. This transformation occurs also during the first hours of aging at 180 degrees Celsius. Afterwards, the phase fraction of aluminum containing beta double prime increases further, up to phase fraction value of 0.009, when a plateau is reached. The number density has a similar evolution. The co-cluster formation occurs during the holding at room temperature, as expected. With the heating to artificial aging temperature, one can notice the formation of beta double prime phase which comes from the transformed co-clusters. After reaching 180 degrees Celsius, some co-clusters are still present, but their number diminishes. Switch the time axis scale to hours in Options window. First, change the axis label from seconds to hours. Next, define the scaling factor for the x-axis. 1 hour has 3,600 seconds, and that will be the factor value, to type. Now, one can see that it takes about 4 hours, maybe 5 hours at 180 degrees Celsius to complete the co-cluster transformation to beta double prime. From that moment on, the number density of beta double prime remains constant. A similar picture is observed for the precipitate mean radius. Beta double prime formation starts during the temperature increase towards 180, and it is still growing together with the phase fraction, as co-clusters are gone. A plateau is reached after about 187 hours of processing, which corresponds to 17 hours of artificial aging.
Ladies and gentlemen, I hope we could demonstrate you how to set up the simulation, in which the co-cluster phase transforms to a beta double prime phase, which is one of the processes that is taking part at the aging of the 6000 aluminum-based alloys. Thank you for your attention. If you have any questions, Feel free to contact us by our support email.